Hi, in part one we looked at this broken DC-DC converter from a 1980s electric car. We identified two shorted transistors and one failed resistor and regained partial function just by disconnecting them. Now we'll try to repair the converter and restore it to full power. So how do I replace these shorted transistors when I don't know what they are? Well, a bit of luck. A friend who also owns a Soleq Evcort found a document from the Department of Energy that identifies the transistors in the switching circuits of the Evcort controller. They're listed as 2N6259, 2773, or 3773. Since the power transistors in the DC-DC converter serve the same switching function, they're probably the same or very similar type. And it probably doesn't matter exactly what transistor is used as long as it has sufficient voltage and current ratings. The whole point of these switching circuits is to minimize dissipation by always having the transistor either fully on or fully off, so the amplification factor shouldn't matter all that much. And finally, I don't think it's critical to match all 20 transistors in the H-bridge. What's important is that all 5 transistors within a bank are as similar as possible, so the current is evenly distributed. I found these two N6259s from Motorola on eBay. They claim 16 amps maximum current and 250 volt breakdown, which should be fine. So I think I'll go ahead and order some of these. So here's the new transistors. They're Motorola 2N6259s. I got a dozen of them. They were about $5 a piece. I couldn't find a 2-watt ceramic wire wound 0.12 resistor, but I found some 5-watt. I got 20 of those. Here we've got this bank has one bad resistor and one bad transistor, and this bank has one bad transistor. So I want to keep all the transistors within a bank the same. So I think the plan is I'll replace all the transistors in this bank with the new ones, take one of the old ones and replace the bad transistor in this bank, and then this lower bank I'll also replace all of the resistors. Okay, I think I've got the technique down for getting out these old transistors. Let's start by taking the screws out. This one has the nut on the bottom. Start by putting a little flux on the terminals. And then we'll try to get the bulk of the solder off with this solder sucking soldering iron. Try to get a little more off with a wick. These pins have got to go through this plastic spacer, so you don't want a big glob of solder on the end. Okay, and then try to get a fingernail under the transistor here. There we go. And it seems like you still have to walk these out back and forth. And it's out. As long as we've got these transistors out, let's compare the two transistors. One thing we can measure is the junction voltages. So here's the OBA transistor, base to emitter 0.52, base to collector 0.51. Here's the Motorola. Base to emitter 0.62. Base to collector 0.61. Well, they're definitely different is about all you can say, so they're not the same transistor. Okay, this meter is supposed to be able to measure the HFE, basically the gain of the transistor or the amplification factor. So here's the OBA transistor. Not really set up for power transistors here. And it says 11. Okay. And here's the Motorola. '86. Well, that's very different, so definitely not the same transistor, but again, I don't think it makes that much difference for this switching application. Okay, so mounting the new transistors is pretty easy. Put on some thermal grease. Just line up the holes. And they slip right in. Okay, so we're all wired up. I've got now 5 OBA transistors gone, replaced with 5 Motorola 6259 transistors. It's interesting, all these say OBA except one. This one says RCA, but looked up these numbers, didn't find anything on that either. And then on this side, 5 new 0.12 ohm resistors in the same bank as those new transistors. This is the lower bank here, but actually on the schematic, this is the upper bank, the bank closest to the positive rail. And then also replace the one shorted transistor in this bank with one of the good transistors that I took out of this bank. So funny thing, if you look at these resistors, this is the one that failed. See how the lettering is all crooked and off center? None of the other ones are like that. None of the other 15 in the converter are like that. Makes you wonder if maybe something happened to this during the manufacturing process. Maybe some hidden flaw caused it to eventually fail. And maybe that caused the transistor it was connected to fail, and that in turn caused the failure of the second transistor. I just think it's pretty rare for transistors to just spontaneously fail. Okay, I think we're ready to power this up, and it'll be the same setup as before. This is output voltage, input current, and the DC source is going to be the traction battery from the car. So let's plug in the sync signal. Okay, it's coming out to 4 volts just like before. And now I'm going to add the DC supply, and this will be through a 270 ohm resistor. Okay, so this immediately comes up to the regulated 14 volts, and it's still 118 volts because it's drawing very, very little current. But now I'm going to add a load. This is a 100 ohm resistor. I've chosen that because it gives the unit just enough voltage to bring this up to 14 volts. So you see the input voltage has gone down to 65. Again, I think there's a detection problem with this meter due to noise in the line. But let's see what this looks like on the oscilloscope. Okay, the oscilloscope ground is on the minus rail, and we're going to look at the collector of the bottom bank of transistors. This is the unmodified bank. And there it is. It's a pretty nice square wave. It looks like it's got some ringing at the heading and tail ends. But basically a square wave. This is 50 volts per division, so it's going up to about 60 volts. So it's giving it pretty much the full supply voltage on each half cycle. Now let's look at the bank with the transistors that we repaired. Pretty similar waveform, but kind of a funny little shoulder here where it goes down to 0 and then comes back up. Maybe not too surprising. These are clearly different type transistors, and they're going to have different characteristics of turning on and off. But again, basically still a square wave. And clearly these transistors are switching on and off as they should. Let's look at the base. I'll turn this down to 5 volts per division. So here's the base of the lower bank of transistors, and this will be the unmodified bank. So pretty much a perfect square wave. Maybe a little bit of ringing at the head end there. So here's the modified bank. So it's a square wave too, but it's got a disturbance that looks like the opposite of what we saw in the collector. And it's at the rising edge, not the falling edge of the pulse. Well, that's because there's a polarity inversion between the base and the collector. When the base goes negative, the transistor turns off, the collector goes positive, and vice versa. So in other words, it looks like the disturbance on the collector waveform isn't because of the new transistors. It's because of the disturbance in the signal from the driver board. Nevertheless, the transistors clearly are switching as they should. And the inverter is clearly working. It's regulating the voltage. Okay, now I'm going to cut out the resistor on the input and connect the 118 volt supply directly to the DC-DC converter. And now I'm going to connect this same 100 ohm resistor as a load. And then again we're getting this rattling noise, which I think is just the choke, but it is still regulating the voltage. So the transistors are clearly working at the higher input voltage. Okay, so this is going to draw about 0.14 of an amp. I'm going to connect a little bit bigger load. This will be a 0.5 amp turn signal bulb. Okay, so same thing, just higher frequency of rattling, so more frequent activation of the circuit here, but it still is maintaining the output voltage. It's drawing like 0.13 of an amp. And now try the turn signal side of the bulb. This will be a 2 amp load. Basically still doing fine. It's drawing almost half of an amp at the input current, giving out 2 amps of output current, so that's about right. Voltage is still stable. This input voltage, again, I think this is just an error in the reading by this meter. So far it seems to be functioning properly. Okay, so finally let's just see what this looks like on the oscilloscope with a 2 amp load. So this is going to be the base of the lower bank in the unmodified transistors. And of course looks pretty much the same as before. It's intermittent pulses, which is what you need to maintain the voltage under these conditions. And here's the modified bank. And of course it looks pretty much the same. Let's go to 2 volts per division. So what it looks like is when it switches the transistor off, it's applying a voltage of minus 2 volts to the base to turn it off. And then the turn on voltage is only about 1 volt. We can look at the collector, but I'm not sure it's going to show anything useful. And again, it's just bouncing around here, and I'm not sure how to interpret that. That's the modified bank. Here's the unmodified bank. Looks pretty much identical, whatever it is. Okay, so I think everything is working fine here. The next step would be to put on a heavier load. 2 amps is still only 1/20th of the rated capacity of the converter. I'm a little reluctant to do that under these conditions because we've got a line to the car that's about 100 feet of extension cord. That's going to have capacitance and inductance that could influence the operation and may prevent these diodes from smoothing out those transients that occur when the transistor is turned on and turned off. So I think what we have to do is get this back up to the car and actually try it in the car with all the loads that it would encounter there, motors and lights and so forth. So let's turn this off for now. Okay, I got this circuit board bolted back down with plenty of thermal grease. But before we think about putting this in the car, I think we have to do something about this Anderson connector here. This is the input for the DC voltage and also the sync signal into the converter. And the wires on here, the insulation has really degraded. It's cracking, looks like it's going to short out any minute. So it's interesting, the same wires, when they come out here on the inside, they're still perfectly supple. And it's just the ones out here that were exposed to the elements that have gotten all cracked and brittle. And anyway, I'm going to somehow have to splice these and put on a new connector here. Well, I got this big piece of shrink wrap off. And now it looks like really it's just this last inch of wire that's degraded. Once you get down to this point, this insulation is fine. It seems to be true for all the wires. So now I'm wondering if maybe I can just slip the pins out of this connector. Well, I absolutely couldn't get any of these contacts out of this connector. So plan B here, I've cut it off with the wires as long as I could. And what I'm going to do is take each wire, take the insulation off back to where it's pliable, And then I can put a 3/32 shrink wrap over that. Then I'll solder on another new a new contact, and then I can slip a 1/8 inch shrink wrap over the whole thing and over the insulation. Pretty tight fit, but it does go on. And that'll be a little better because I'll have a double insulation here. Okay, I got these contacts all soldered on and shrink wrapped. I was even able to retain the original color coding here. So just gotta get these fitted into these connectors. Okay, got the connector all assembled here. Looks a little bit safer than before. Just about ready for a test. Okay, just a final check here before we put it back in the car. Here's the sync signal. 4 volts. Supply the DC. $14 volts. Let's eliminate the resistor. Little overshoot. Here's the 1/2 amp load. Looks the same. Two amp load. Little noisy, but its voltage is stable, current is stable. I think it's fine. Okay, let's shut it down. I think we're ready to put it back together. Okay, we're ready for a test here. I've got the high voltage DC line plugged in. I've got these connectors connected straight to the battery. A funny thing I noticed, there's 2 connections coming out of here. One is this is supposed to go to the battery. This is supposed to go to the electrical system. And the battery one has a fuse. This one doesn't have any fuse at all. That is the one going to the electrical system. So I put in my own fuse, a 20 amp fuse. So it can only go up to 20 amps, but we're going to give it a test here. So as always, this is measuring the electrical system voltage. This is going to measure the current. Let's turn it on. And looks good so far. It's holding 14 volts, 9.5 amps. That's the vacuum pump for the power brakes running and squeaking there. Wait till that stops. Okay, I'm going to turn on the lights. Voltage has dropped a little bit, drawing almost 20 amps. Well, 18 amps. And that's about the limit of my fuse, so I think I'll stop here for now. Okay, I think we're ready for another test here. Same setup, volts, amperes. This is now a 40 amp fuse. I'm going to turn on the ignition. Looks good, 14 volts, 10 amps. I'm going to take a temperature reading on the heatsink here. 55 degrees. Okay, let's turn on some more accessories. There's the lights. Now we're doing 18 amps. I'm going to try the heater. Actually, just the heater fan motor. Now we're drawing 22 amps. We're still above 14 volts. Heatsink still 55. Okay, I'm going to turn the lights back on. Okay, 31 amps. We're nearing the capacity of the converter, and we're just a bit below 14 volts. See if this is heating up. Now it's about 57 degrees. Doesn't feel warm. Okay, one more thing, turn on the wipers. Okay, 34 amps. And I'm just going to leave that go for a while, see if it can maintain it. It is heating up a bit. Now it's about 60 degrees Fahrenheit. Okay, we're 15 minutes later now. Everything looks pretty stable. Voltage has dropped maybe a tenth of a volt. I think that's just because the transistors have warmed up here. Started out at 53, now we're up to about 96. That's about 35 degrees C. Of course, I don't know how hot the transistors are, but I doubt they're getting heated anywhere near their maximum rating. Current is going down just a bit, probably because the voltage has gone down. But everything still looks pretty stable. Okay, we're briefly hitting 36 amps now because of the air pump for the power brakes. Okay, been going 30 minutes now. Everything's still stable. Voltage has dropped maybe another 1/10 of a volt, so maybe 2/10 of a volt total in 30 minutes. Again, I think that's just because it's warming up. Let's get a final temperature reading here. So now it's up to like 116 degrees Fahrenheit. About, that says 47 centigrade. So I'm sure it's supposed to heat up a little bit. If it weren't, they wouldn't have the big honking heat sink on there. So I think it's basically working as designed. And I think at this point I'm going to shut this down. So as far as I can tell, everything's working well. It's not getting excessively hot. It's regulating the voltage well, putting out very near its rated current, and that's about all you can turn on this car. Now whether I reinstall it, I'm not sure. I did a lot of modifications down here when I put the Xenon converter in, put in a bigger battery, put in this little shelf. So there's a lot of things I'd have to change. I would like to try it in the car, but now I'm thinking maybe I'll go ahead and see what I can do with the controller first. But anyway, looks like a successful repair. If there's some flaw still in there that I didn't catch, that's going to make it fail again soon, I don't know. And the only way to do that is put it back in, drive it around, use it every day. But for now, I think this is a successful repair. Thanks for watching.